Welcome back, everyone, and welcome to the first of two videos on the topic of probability. Probability will be a tool that we are going to use in statistics to help us make decisions. So we're not going to actually go into a lot of depth about probability. It's its own mathematical field. Instead, though, what we need is a nice, solid understanding of the essentials of probability, what probability tells us, and how it's computed. In this particular video, we're going to focus on the concepts of empirical versus theoretical probability. So we'll see how to determine the probability of an event, how to use that probability to decide how likely something is to happen, and then we'll look at a couple rules that will help when we're trying to make these computations. So the first example, it's a completely made up example, but suppose that in front of me right here, which you can't see, I have a bag that contains 327 marbles. And suppose someone comes over here, closes their eyes, puts their hand in the bag, mixes the marbles around, picks one marble, pulls it out of the bag, then opens their eyes and look at the color. I want to know, what's the probability? What are the chances that that marble is going to be green? Now let's not worry about how to actually come up with a number yet. Let's just figure out, well, what kind of number do we want? And it's very straightforward. We want a number between 0 and 1. The closer the number is to 0, that's going to indicate the less likely we think that that event will happen. On the flip side, the closer we get to 1, then the more likely we think that's going to happen. So you can think of, in terms of weather reports, there is a 80% chance of rain today. 80% is actually a number that lives between 0 and 1. 80% is 80 out of 100, 0.8. And when the weather person says it's an 80% chance of rain, then we feel like there's a very good chance that it actually will rain today. Versus if they say there's a 10% chance of rain, then we feel like, maybe we won't bring an umbrella or a rain jacket with us. So again, very important to understand, probability is going to be a number. The closer you are to 0 means that the less likely we think it's going to happen. The closer the number is to 1, the more likely we think it's going to happen. So how do we actually get a number for this, especially since you can't see the bag because it's in front of me and you can't see me? Well, one way to do this is very statistical in nature. We don't know something, we go out and collect data. So in probability language, we call this empirical probability. We go out and actually do this activity. So I'm going to actually go in and close my eyes, reach in, grab a marble, and then look at the color. And I'm going to do this several times. And I'm going to keep track of the color of the marble that I pull out. So I go out and collect data, and then I'm going to create a ratio based on this data. The mathematical language here, that P with the A in parentheses, the P stands for probability. It's like if you remember back to an algebra class, the name of a function. So P is the probability function. And the inside parentheses is kind of like the input. What are we trying to figure out the probability of? So in this case, A is just a generic event. We're going to create a ratio. We're going to count how many times A actually happened out of how many times we attempted this. So I'm going to put up some fake data here. So suppose that I went and I did this activity 24 times, reaching into the bag, grabbing out a single marble, looking at its color, writing it down, putting it back in the bag, mixing it up, all that. The data's in front of us. How do we compute the empirical probability? I'm going to count how many times I see green. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is one of those qualitative variables, yeah? So, this very much feels like, what was that table? We called it something like a frequency distribution. Yeah. Except we're not looking at all the colors, we're just focusing on green, and the frequency of green was 5 out of 24. So we're going to say that the probability of selecting a green marble is 5 over 24, which is approximately 20.8%. So we're using this data to make our approximation. It's important to note here that if I did this tomorrow and I did it 30 times, I might not get exactly 20.8. So the 20.8 is an estimate based on data that was collected. You might be wondering, how come we don't just look at all the marbles that are actually in the bag? That would make a lot of sense. But 327 marbles, that's a lot of marbles to have to count. And it's like doing a census, right? And doing a census is always prone to some kind of errors, and 327 is a lot to count. So now let's look at a bag that doesn't have as many marbles, but look at the other way of computing a probability. So assume that we have a bag with 12 marbles, and we can actually look in there and do a census. We know that there are 4 pink, 6 yellow, and 2 green. That census is actually called a sample space in probability terms. It's a listing of everything that is in that bag. And what we can do is use letters and numbers, in this case letters and subscripts, to identify what's in that bag, especially when we have multiple of the same. So P with the 1, that's P sub 1, means that it's the first pink marble, but we also have 3 other pink marbles that are identical. So we just identify them as P sub 1, P sub 2, P sub 3, P sub 4. The same thing for the yellow and the same thing for the green. So we know what's in the bag. If we reach in the bag, we know that we have to pick one of those 12, right? So this is where we do what's called theoretical probability. So we're going to say, hey, if they're all the same size, shape, texture, then when I reach in that bag, all of them are equally likely. And this is kind of where theoretical probability differs from empirical, because theoretical is treating all these items in the sample space as equally possible. So to compute theoretical probability, we're also going to do a ratio. This time we're simply going to count the number of green marbles that are in the sample space and divide that by the total number of items in the sample space, in this case 12. So we get 1 out of 6. What's nice about theoretical probability is that since it's based on a sample space, it doesn't matter if I do it today or tomorrow or someone else does it. We're all going to agree on the same answer because we'll all be looking at the same sample space. With empirical probability, different people doing different numbers of trials are not going to get exactly the same number. They're probably going to get in the same ballpark. So a natural question at this point that you're probably asking is, I don't get it. Why are there 2 different ways of doing it? Why don't we just learn one way? Sometimes, as you saw with the bag of 327 marbles, getting the sample space might not be easy. It might be easier to collect data and do the empirical way. So how do we reconcile these 2 different methods? And we do this through what's called the law of large numbers. So let's look at an example of flipping a coin. Suppose I wanted to calculate the probability that it would land heads up. The empirical method, I could say, well, let me flip the coin 3 times. It landed heads up once. So I'm going to estimate the probability to be 1 out of 3, or 33.3%. Someone doing the theoretical is going to say, well, if you flip a coin, there's only two things that can happen. It's either going to land heads up or it's going to land tails up. So the theoretical probability is 1 out of 2, or 50%. So we see we're not getting the exact same values here. The law of large numbers, though, says that if the empirical person had done more flips, the more flips you do, then you should be approaching the same value that the theoretical person is getting. So what if I had flipped the coin 1,000 times and I got that it landed heads up 508 of those times? Well, now my empirical probability is 508 out of 1,000, which is about 50.8%. So you can see now that the law of large numbers is really saying that if the empirical person just collects more data, they should match up with the theoretical person. Let's now look at a completely different situation. Get rid of the marbles and let's talk about ping pong. So let's suppose that Mrs. Smith and her son are about to play a game of ping pong. And we want to know what's the probability that Mrs. Smith will win. So as a reminder, we're looking for a number somewhere between 0 and 1. 0 means definitely will not happen. 1 means it definitely will happen. Now remember, there's two ways of computing probability, that empirical versus theoretical. So let's look at the theoretical. What would the sample space look like? Well, there's only two things that can happen. Either Mrs. Smith wins or she does not win. So probability that Mrs. Smith will win is 50%. This doesn't seem right. So this goes to demonstrate that sometimes theoretical probability is not necessarily the best way to compute a probability. So this is a good time to say, let's go back to empirical probability. Let's go collect some historical data. Turns out Mrs. Smith has won 16 of the last 20 ping pong games against her son. So we're going to use that empirical data. We're going to use the data from the past and say, hey, 16 out of 20 is my ratio, 4 out of 5, about 80%. So empirical probability here makes much more sense as a way of computing a probability in this situation. Sometimes we ask more complicated questions when dealing with probability. Sometimes we combine some events, like in this example. We're asking, what is the probability of rolling a number that is even or less than 5? Individually, those are separate events. So how do we compute the probability of this combination of these two events? To do this, we're going to turn to the addition rule. Very handy to have. The addition rule says that you can focus on the individual events, but then at the end you have to subtract any double counts. So let's see how this works. Probability of rolling an even number, looking at the sample space, we get 3 out of 6. Probability of rolling a number less than 5, again looking at the sample space, probability is 4 out of 6. So if we add those two probabilities, we end up with 7 out of 6. Well, we don't like probabilities that are greater than 1. Probabilities are, remember, numbers that have to be between 0 and 1. So in this situation, we need to subtract any of the numbers that were both even and less than 5. So if we look at the sample space, the numbers 2 and 4, they got double counted. They got counted as being both even and as being both less than 5. So we need to remove that double count. So we're going to subtract away the probability of getting those even and less than 5. So subtract away the 2/6 from the 7/6, and we get our final correct answer of 5 out of 6. This addition rule is actually going to come in very handy in the next video when we start looking at sample spaces that are a little bit more complicated and we want to avoid double counting. The only other rule that we're going to look at in this course is what's called the complement rule. This is a way of figuring out the probability of an event not happening. So the way we think about this, an event either happens or doesn't happen. It's got to be one of the other. So going back to our bag of marbles example, if I wanted to know the probability of selecting a marble that is not green, well, I could count in the sample space how many are not green. But the tricky way of doing this is to say, well, let me actually just count how many are green. I've got 2 green out of 12. So the probability of selecting a green is 2 out of 12. That means that the probability of not selecting a green has to be whatever's left over. So I take that 2 over 12 and I subtract it away from 1, or the probability of selecting a marble that is not green. The homework is designed to get you to really think about the basics of probability. So definitely spend some time on it. And then we'll see you on the next video where we'll dive into what are called two-way tables.